We describe an approach for matting and compositing transparent and refractive objects from photos. Starting with an input image like this, we are able to matte out the transparent object and place it in a new image. We can also achieve effects such as placing multiple objects into a scene, simulating scene depth, simulating caustic shadows, and even simulating a Fresnel lens effect to enhance boundary realism. Our appearance model makes two assumptions. First, each transparent object has specularities caused by illumination outside the scene. Second, only the visible part of the background is deformed by the object. Note that we also account for light attenuation. The key to editing transparent objects is the Attenuation Refraction Matte, or ARM. ARM consists of four components: Object Mask M, Specular Alpha Matte, Transmission Factor Beta, and Refractive Deformation G. The object mask is used to isolate the object from the input image. From this region, an alpha matte is used to describe the specular highlights. Remaining effects are described using a color attenuation term beta and a deformation field G that describes how to warp the background scene. We now show how user markup can be made to extract an object's arm from a single image. We use the technique of lazy snapping to allow the user to extract the object's mask. The user draws scribbles inside and outside the object to recover the mask. To extract the specular alpha mattes, a trimap can be automatically generated via thresholding, with manual adjustments made if necessary. Poisson matting is performed to produce the specular alpha matte. This matte can be further touched up if needed. The user then specifies a transmission factor beta by marking up background colors and their corresponding attenuated colors in the object. To specify the refractive deformation G, the user marks up stroke pairs where a reference stroke is first drawn followed by its target stroke. There are two main visual cues that can be used. Foreground cues are where reference strokes are drawn on the background, and target strokes are drawn to follow the foreground shape as shown here. Background cues are where a reference stroke is drawn on a visible feature in the background, and the target stroke represents how it's deformed by the object as shown here. The object now can be extracted and placed into a new image. The refractive deformation markup does not need to be accurate, and significantly different markups can still produce good results. Here we show an example where two different markups are being drawn for the dragon. Even though the markups are significantly different, they both produce equally plausible results. Here we show a series of objects extracted by our approach. Given the extracted object, we can produce a variety of compositing effects. These include simple cut and paste, simulating scene depth, simulating caustic shadows, Fresnel lens effect to enhance boundary realism, and multiple object compositing. Cutting and pasting simply requires the application of the arm onto a new background. Varying scene depth can be simulated by scaling the arm's refractive deformation to cover a smaller or larger portion of the background. Caustic shadows can be simulated using the refractive deformation G to find where light converges and diverges. A Fresnel lens boundary effect can be simulated by enforcing gradient constraints from the input image on the object's boundary in the composite image. Our compositing equation easily extends itself to compound refraction when multiple objects are pasted, as shown here.